Hello, in this video I'm going to stay on the topic of energy because there's some terminology around fields and potential that we need to clear up in order to understand potential energy concerning fundamental forces, our non-contact forces. So far we've only really been looking at gravity there. Gravitational fields, gravitational potential energy. So here we just need to clear up those terms to understand what we really mean. Right, so first of all, what's a field? A field is a mathematical description of how some quantity is changing in space. So say we've got some volume here, some volume of space. Doesn't really matter what it is. I'm just trying to section something off. Then we could say inside this volume, every single point that we pick, an infinite number of points that we've got on there in there, every one of those points is going to have some value associated with it, and that'd be it if it's a scalar field. If it's just a scalar field, such as how does energy vary across this space, then each point will just have a value associated with it, just some number. If it's a vector field, then each point will have that value, that magnitude, and it'll also have a direction. So a vector field could be a force field because forces are vectors. So every single point will have the magnitude of the force and the direction that the force is acting in. So that's all that fields are. Fields are just a way of describing how these things, vary across some space. So let's take an example then, seeing as we're looking at gravitational fields. So say we had put some mass inside this field. So we've got some big object sitting somewhere. I don't know, maybe we've got the Earth sitting right at the middle of this space, and then we put some object inside the gravitational field of the Earth. So at that point, we're going to need a direction of the gravitational force, which is going to be towards the Earth, and we're going to need the magnitude of the force. And the magnitude of the force, we know we can calculate using Newton's law of gravitation, using F equals gmm over r squared. So that's telling us the force experienced, the gravitational force experienced by a particular object inside the field. But what if we want to define or describe the gravitational field of an object just all on its own? So say we hadn't put this object there inside the Earth's gravitational field, we just want to describe the Earth's gravitational field. Right, well, we can do that by generalizing and dividing by the mass. So we're going to talk about force per unit mass at every point in space. So force per unit mass is then G capital M over R squared. So you can see on the right hand side, this has got nothing to do with this second object. It's just got the mass of the Earth, and it's got what distance we are away from the center of mass of the Earth. So that is only concerning the Earth itself and its gravitational field in space. And then on the left hand side, we've got this force per unit mass, which we're going to describe as the gravitational field strength. So we've just generalized this, removing this need for a second object. And now we're just describing the Earth's gravitational field on its own. So we can do a similar thing if we then move from force, as we've been looking at here, describing this force field, into potential. So now we're moving into a scalar field because potential is to do with energy. So let's think about what's happened to the energy of this object. Let's go back to this specific case of having an object. So to put that object into the Earth's gravitational field, the object would have started off at some distance, infinite distance. It's as far away from the Earth as it could be. It's experiencing no force whatsoever at that distance because it's so far away it can't feel the gravitational effects of the Earth. We then move it from this infinite distance away to some distance r away from the Earth. So work has been done because a force has acted through a distance. So we remember back to our earlier video on the work energy principle. The work done is the force multiplied by the distance, which is equal to the energy transferred. So the work done is the energy transferred. Now, it's the force multiplied by the distance if the force is constant. But of course, the force is changing here because the force itself is a function of the distance. So we're going to need to accumulate up how the force is changing on this path from infinity to a distance r. So we're going to have to integrate the force over the distance as it moves from a position infinitely far away to a position just r away from the center of the earth. So we need to perform that integral to see how much work has been done on the object. Now we know what f is as a function of r. We can just drop that in, and then we can perform an actual integral. We've got gmm over r squared dr. So we've got three constants on the top. So we're just going to be integrating that in order to get what we're going to get. We're going to get minus gmm over r. And that is going from infinity up to r. Now, of course, when we put infinity in, we're going to get infinity on the denominator, which means that that's just going to disappear. So we're going to get a final result of minus gmm over r. So that is the work that has been done on the object, moving it there. So it's now located, if it's just sat at that point in the gravitational field of the Earth, so that is then potential energy that it has. It's not moving, so it's not kinetic energy. It's potential energy. And the potential energy is equal to minus gmm over r. Now it's minus because we haven't actually had to do, we haven't had to expend effort in order to get that object there. Gravity is an attractive force, so the object, once it starts moving, it's just getting pulled in. It's getting pulled in towards the Earth. So we're actually doing negative work here. The object is losing energy as it moves closer and closer to the Earth. If we were moving it in the other direction, then that would be a different matter. If we were now dragging that back out to infinity again, we're having to put energy into the object in order to take it away from the Earth. But in this case, we didn't have to. So that's why we've got that minus sign there. If we were going in the other direction, we'd be going from r to infinity. We flip the limits on our integral, and then we'll get a positive answer. So that's all built into our calculus here. Now that we've got this specific energy here, so this is the potential energy, that's our gravitational potential energy of a particular object. We can do the same sort of generalization as we did before, where we divided through by the m to say rather than have force, we'll have force per unit mass, because now then it would be independent of that object. We'll just be talking about the gravitational field strength. We can do the same thing here. So we can move from talking about the gravitational potential energy of this specific object, of this thing here that we've placed in the field of the Earth, and just talk about the gravitational potential on its own. So the gravitational potential is then the energy per unit mass. So we're dividing again. So we're going to say, well, the potential, the gravitational potential, it's going to move up here as I've taken up a lot of space. The gravitational potential is the energy per unit mass. Energy per unit mass, and that is going to be equal to minus gm over r. So that is then our potential field. That's a scalar field. It's energy. So our GPE is in units of joules. Here we've moved to gravitational potential energy, gravitational potential, which is joules per kilogram, because we divided by mass. Here we had our force, in newtons, and then we've gone to newtons per kilogram, force per unit mass. So this idea of potential is energy. That's what you want to be thinking of. It's a generalized way of describing an energy field. So we'll be able to use the language of potential difference. I mean, this is something that you might be familiar with in electricity. You're looking at potential difference. How does the energy change from one point in a field to another point in the field? But it's generalized because, again, we'll be making, in the case of electrical energy, we'll be dividing by the charge. So it would be energy per unit charge. Here we've got energy per unit mass. So we're just generalizing it out. So we're talking about this scalar field of potential energy independent of the objects that are placed in it. Then when we place an object in it, we can take our gravitational potential, multiply it by the mass of the object we're placing in the field, and then that gives us the gravitational potential energy. So there's a lot to take in there in terms of terminology, but hopefully it's clearing up, what a field is. We've got vector fields and scalar fields, and that's just describing how some quantity changes in space. Then we're looking at force fields, which is our gravitational field strength. That is our force field. And then we're looking at energy fields, which is our gravitational potential. So they're the 4 things, or 3 things, however many it was, that you want to take out of this. What a field is, and then we've got a force field and we've got an energy field. And we're just looking at how those 2 things change in space.